In this module, we will start discussing a touchstone quantum phenomena of two-dimensional system, that is the quantum Hall effect. So before we dwell into the details, let us quickly and briefly review the classical Hall effect, which was discovered by Edwin Hall in 1879. So what you have here is you have a conducting material and you have a magnetic field which is applied at the perpendicular plane, normal to the plane, and you have an electric field along the plane of the sample. And the transport of electron is driven by a lot of collision process as described by the Drude picture, Drude's theory. Now the electron will undergo cyclotron motion, but at the same time electron will undergo many collisions, and eventually the electrons will get deflected towards one edge of the sample, and other edge you will have the positively charged ions. And at some point of time, a balance will be reached by the field generated by the exposed ions and the collected electrons, and no more electrons will be actually collected, and there will be a steady state where a voltage is generated across the edge, that is the VH, the Hall voltage. And from this Hall voltage we can get information on the carrier concentration in the sample, and we can also extract from the carrier concentration we can extract mobility, conductivity, and all these details. Okay. Now in this lecture we will go through the mathematical formalism of the Hall effect briefly. Then we will define the resistivity tensor and overview the quantum Hall effect, and we'll look into the quantum Hall effect in graphene and how the quantum Hall effect is used as a universal resistance standard. So that is the plan for this lecture. Okay. Then next lecture we will look in the mathematical formalism of the quantum Hall effect. Now how are we getting the quantized resistance and all those details in the coming lectures. Okay. All right. So this is the picture of the sample where you have a magnetic field which is applied perpendicular, and there is an electric field which is driving the current Ix. Okay. And the quantum Hall effect actually is slightly different. That applies to a two-dimensional system, but in this case we are considering it's a three-dimensional material. Okay. The normal Hall effect, what you have is you have a B field and you are plotting the Hall voltage or the Hall resistance. If you divide the Hall voltage by the current, then you will get the Hall resistance. Then you will get a straight line. That is, the Hall voltage is proportional to the B field. Now the assumption here is the carriers undergo scattering with various scattering centers inside the material, and the momentum lost during the scattering is actually momentum received from the field, and this is the condition for the steady state. And you have the equation of motion here. This is the force mvd by tau m. Okay, vd is the drift velocity, tau m is the scattering time, or that is the force experienced by the charge carriers. Okay, and that is a force exerted by the electric field, and this is the force by the magnetic field, V cross B term and E. This is the force to the cross field. Now what we are doing here is we are going to look into the action in terms of the various components of this field. We have field separated into the x, y, and z component, the velocity, the drift velocity, vx, vy, and vz, and the b field, which we have applied only in one direction, that is the bz. That is the only component I am going to consider. Okay. And once we substitute these three in this equation, you can generate this matrix. Okay. So I have marked a small square matrix inside this, as 2 by 2 square matrix inside this. That is what is going to be relevant for a two-dimensional system. Eventually, that is what is going to decide the whole voltage and Hall effect, because the moment you apply magnetic field, all the action of the electron happens in the plane, whereas the direction along the field or parallel field is not going to get affected by the field. So there you will not see an effect of field, okay, in that component. Now, when you, as I told, when you substitute these equations into this equation, you will generate this matrix equation, and from this matrix equation, you can generate this one by substituting J equal to NE into VD. J is the current density. J has the components Jx, Jy, and Jz, and VD has the component Vx, Vy, and Vz. Okay. So the aim here is we need to replace this with the Jx, Jy, and Jz component. That is only change when you go from here to here. So here you take this V's and replace those with Jx, Jy, and Jz using this equation. And you do some rearrangement, and eventually you will get m by ne square tau, okay, into this matrix. The J matrix is going to give you E. The J vector is going to give you the E vector, electric field vector. Okay. And this is basically equal to the formalism E is equal to rho into J, that is the Ohm's law. Okay. Where this rho is nothing but the resistivity, J is the current density, and E is the electric field. Because you are familiar with the Ohm's law in terms of the conductivity, but this is just resistivity. So what you are familiar with is J sigma into E, okay, and this is just the sigma is replaced by 1 by rho. That's, then you take that rho to the other side. Okay, that's what it is. Okay. So here, what you have now is, you have this rho, the resistivity, as a tensor. It's a resistivity tensor because it has components in all the direction. Okay. So it's a 3 by 3 matrix. M by ne square tau is the resistivity when you have no B field, or when the B field is 0, and this is an isotropic quantity when you don't have any B field. The moment you turn on the B field, you're going to get this off diagonal components. Okay, those are proportional to B field of diagonal components. The diagonal ones are independent of the B field. Now, as I told, the third row and third column, which represents the component which involves the Z direction, we don't need to consider because field doesn't do anything in that direction. The magnetic field doesn't do anything in that direction to the charge carrier. So for the time being, to ease the discussion, we can ignore that and we can just take the matrix, which is the 2 by 2 matrix here. And that resistivity is given by m by ne square tau into this matrix inside. And this is of the form, you have rho xx, rho xy, rho yx and rho yy. These rho x, y and rho yx, the off-diagonal components which involves magnetic field, and the diagonal components which are your normal resistivity, which is equivalent to your Ohm's law derivation using the classical Drude's theorem. This is the normal resistivity, and the off-diagonal components, the rho xy and rho yx, the rho xy is negative of rho yx, is B by Ne, that is the Hall resistivity. Okay, and the Hall resistivity is proportional to B and it is inversely proportional to N. So directly from this slope you can calculate the carrier concentration from here. This is proportional, the Hall resistivity. So Vh by I, that will give you the R rho xy. Okay, that is your Hall resistance. Okay, now that is proportional, that the slope of that is proportional to the B field. Okay, but at the same time the longitudinal resistance does not have any dependence on the B, whereas only the transfer resistance has a dependence. Longitudinal resistance is the resistance along the propagation, along the direction of the applied electric field, and transverse is the one which is normal perpendicular to, that is the xy term. If we assume the electric field applied in x direction, magnetic field is the direction I'm discussing, or I'm talking about xy direction. The xy direction, that is proportional to the B field, and this is the classical Hall effect. All right. Now, if you do this experiment, the same Hall effect experiment in a two-dimensional system, a clean two-dimensional system, okay. When I say clean two-dimensional system, it has ample mean free path, so that the electrons which are undergoing the cyclotron motion can complete the full circle, at least one full circle. Okay. Now, if you do this experiment in clean system, you will, the clean in two dimension, it's a two-dimensional system, is going to reveal a slightly different Hall effect picture. So that is the quantum Hall effect. Okay, that is a quantum mechanical counterpart of the Hall effect. Okay, so I will briefly review. I'll give you an overview of what that effect is in this class. Now, how that effect is used in certain technology is called the quantum electrical metrology. In quantum electrical metrology as a resistance, universal resistance standard. The quantum Hall effect was discovered by Klaus von Klitzing in 1980, which earned him the Nobel Prize. So this is an extract from his lab notebook, von Klitzing lab notebook, which is the birth of the quantum Hall effect. So here what we have is a silicon dioxide and metal. There is a MOSFET, okay, and this is the top view of the MOSFET, which is a classical Hall bar geometry. So for the time being, what you can assume is you have electrons or you have charge carriers wherever you are seeing these lines or these bright regions. Those are the basically gates. You can think, okay, where you have carriers in those regions. Okay, so what you have is when you apply voltage onto the gate and you have a silicon substrate, it's a MOSFET, you're going to create a thin accumulation layer which looks like a quantum well, which is actually a quantum well, triangular shaped quantum well at the interface. You have charge carriers here. This is low energy region for electrons. Your Fermi level is somewhere here, and you have a triangular well, and the well thickness or the width of the well is such that you have only one quantum level populated below the Fermi level. That is actually a two-dimensional system where in the direction, in the z direction, which is perpendicular to the plane of this substrate, you have only one momentum state, or there's only one k state. So then you can assume that that's a two-dimensional system. Okay, but the charge carriers, as we discussed in the gallium arsenide, aluminum gallium arsenide two-dimensional system, the charge carriers are free to move in the plane, but they cannot move. There is no momentum state available for the charge carriers to scatter in the z direction. Okay. Now, the experiment is as follows. You have a B field which is applied perpendicular to sample, perpendicular to this material. Then what you do is you vary the gate voltage, which will change the charge density or carrier concentration in this well. Okay, so you have carriers in this well, and you are going to change that carrier concentration, which I have labeled NS, which is linearly related to the gate voltage. It's you can think it's like a capacitor, where you are applying a voltage on this capacitor plate, and the second plate of the capacitor is the two-dimensional electron system. So the number of electrons, which is the charge Q on the capacitor plate, is basically proportional to the voltage on the capacitor plate. Okay, that is the gate voltage. Now, usually, as far as Hall effect is concerned, the classical Hall effect is concerned, until this phenomena was discovered, you have Rxy is B by E into NZ. That means when you vary the carrier concentration by the gate voltage, that there should be a reduction in the Rxy, which is the Rx, the Hall resistance. So what is expected as per classical physics is this linear shaped straight line. Okay, it's a straight line. Now what was observed is something like this. So if you look this graph carefully, let us focus on this curve. Let me try to draw on top of it. So this one, then you have step region, another step, this curve. Okay. So I have kind of tried to give you a feeling of what the curve is going to look like. You have flat, we have step-shaped curve, and this is a magnified view from that curve. Okay. So you have a flat region, is a step at quantized certain value RH, which are given by this formula, where nu is an integer. Okay. So what you have is, you have a step-shaped curve instead of a straight line, where the step values are actually quantized in h by e squared. That means the highest value is h by e squared, and the other steps are 1 by nu of h by e squared. Okay, where h by e squared is the resistance quantum or quantized resistance value, which is equal to 25.8128 kilo. Okay, so this is the quantum Hall effect, where the Hall resistance is quantized in h by e square. I would say conductance is quantized because Hall resistance is 1 by nu, where nu is an integer. Okay, nu is an integer. Okay, So it is RH is quantized in 1 by nu, where nu is into h by e square. Okay, this is the quantum Hall effect. Now, this was done in silicon MOSFET geometry, in silicon at low temperature. Okay, so you can see that this is done at really high field. Okay, and even what time is also marked, is around 2 a.m. Early in the morning. Okay, which earned him the Nobel Prize in physics. Okay, this discovery happened in 1980. Now, what we have from the previous slide is we are varying the Rxy by varying Ns. But instead of that, you can also vary B field, the magnetic field. So the later generation of high mobility material based on the gallium arsenide, aluminum gallium arsenide or similar system, those are remotely doped. They already have carriers in the well, in the quantum well. The formation of the well we have discussed extensively in one of those modules. Okay, so you have again similar geometry where you are injecting current and you are measuring the voltage across or perpendicular direction of current where the magnetic field B is applied perpendicular plane. Okay, and this data is taken using one of those samples, and what you are seeing here is the Rxy, the Hall resistance, is showing a step-like feature as shown here. Okay, this Rxy. Okay, now at the same time you are also seeing a Vxx, the voltage along the x direction, which is measured across one of these probes in the direction of the current propagation. Okay, and that is also showing oscillation. Okay, so this oscillation in the current in the direction of the field is called Subnikov-DeHaas oscillations, and this is the quantum Hall effect, the step-like feature in the Rxy. And you can see this is one of the high field behavior. Here is the low field behavior. Okay, the high field behavior, you can see that you have plateau at n is equal to 1. This axis you have to map back to here. This is the axis that is around 25 point, no, it's not around, it's actually exactly 25.8138, and the second one is here, half of it, and third one is here, and so on. Okay, and there are also oscillations, the red colored curve in the Rxx, that is a linear resistance or resistance along the direction of the field. So if I mark it here, Rxy will be this, and Rxx will be the resistance in this direction. Okay, in the direction of the field, electric field. Okay. Now, a few years later, as the technology of making higher and higher mobility material got matured, the experimentalists start observing a slightly complicated, intricate Hall effect that is called fractional quantum Hall effect. Okay. In this case, you have plateaus or flat regions in the Rxy, but not only at integer values, but also at various fractional values as marked here. This, if time permits, we will discuss in one of the classes, but it's not going to be discussed in detail anyway in this course, which is beyond the scope of this course. Okay, but this is called fractional quantum Hall effect, where you have resistance quantized at fractional values, certain fractional values such as one third, 2/5, 7/3, 9/4, and all these values, okay, which are marked here. That earned a second Nobel Prize for the quantum Hall effect phenomena. Okay, the first one was for integer quantum Hall effect. The second one was for the fractional quantum Hall effect. And this is a very fascinating phenomena whose physics is kind of very different from that of the integer quantum Hall effect. So to put it briefly, integer quantum Hall effect is something which you can explain using single particle picture, but fractional quantum Hall effect is a many body phenomenon. Okay, there are fractional states, there are composite particles. Here you have electrons, but in this case you have composite particles. Okay, so that is a many body. There is a many body phenomena, whereas this one you can explain with the single particle picture. Okay, and that we will explain during this course. Okay, now the difference here is, in this case we have varied the carrier concentration by fixing the B field. In this case we have fixed the carrier concentration but varied the B field. But anyway, the ratio between the magnetic field and the carrier concentration is what we have varied. Okay, now the advent of the new generation two-dimensional systems, the first one being the graphene. It is a sheet of carbon atom, and one of the first experiment after extraction of a sheet of carbon atom, after extraction of sheet of carbon atoms from graphite, is the magnetotransport, where you apply a magnetic field perpendicular to plane of the sheet, where you have a backgate which is highly doped silicon, and there is a silicon dioxide gate oxide. Then you have the sheet of graphene, then is patterned to form in the form of a hole bar. This is the top view of that. Okay, and when you conduct the same experiment where you measure the transverse resistance as a function of magnetic field over carrier concentration. So in this case, the magnetic field was fixed at 14 Tesla, and the carrier concentration was varied by varying the gate, the back gate. Okay, when this experiment was done, then also they observed a step-like feature as opposed to a straight line in the Hall effect. And of course, they also observed oscillation in the RXX, that is the green curve here. This experiment was done at 4 Kelvin. Okay. Now, this red colored trace represents the Hall resistance, and that also shows step-like feature and is quantized. If you look at carefully, the unit here is 4 E square by h, okay, instead of E square by h. And the detailed physics, if time permits, we will discuss, but that has to do with the nature of these charge carriers. Those are not the normal conduction band electrons that you find in this kind of free electron gas, the silicon or gallium arsenide material. Here you have a Dirac particle, massless fermions, and you have valleys, and you have spin degeneracy. All these, because this is not a really high field, all this together is going to give you a slightly different Hall effect, but still it is quantized. The resistance is, Hall resistance RH is quantized. That is the point. It's quantized in this picture also. And surprisingly, this effect was observed even at room temperature. Okay. you can find more details about this in these two papers. Okay, and I would say that is probably, I can say it's a third Nobel Prize for though it's not directly for quantum Hall effect, but the feature that demonstrate in this experiment is the quantum Hall effect. Okay, it's probably the third Nobel Prize for performing a quantum Hall effect experiment. And interestingly, you can see this quantization even at 300 Kelvin room temperature in a sheet of graphene. That is awesome. Okay. So what we have now is, you have seen this effect in starting from a silicon MOSFET. Then we moved on to gallium arsenide heterostructure, two-dimensional electron system. There also use the same effect. And now there is another completely different two-dimensional system. It is radically different. Those are bulk two-dimensional system or interface in the bulk material, the first two ones. But this is actually a sheet, a pure sheet of atoms. There also you are seeing the same effect, the quantization, and it's so robust. So what we now need to realize is this quantum Hall effect is a universal phenomenon. It doesn't depend on material system. Okay, it doesn't depend on the kind of equipment you use. It doesn't depend on the temperature. As long as certain energy scales are met, you will see this effect. So, and this was initially proposed, and now this has been widely well accepted and followed as a resistance standard, universal resistance standard in quantum electrical metrology. So this is a picture of one of those samples. It's a gallium arsenide sample, but this has been done on various materials and verified across the world, across the countries, that this is such a robust phenomena. And the plots here are the errors that are measured in these quantized values of resistance. Those are in nano ohms. Okay, that 9th place after the decimal. Okay, all these are in nano ohms. If you read the axis carefully, these are all error that has been, variation that has been measured over various systems. This is not even like 1 nano ohm. Okay, this full scale here is like 3 or 4 nano ohms. Okay. Now, in this case, okay, so here is a 200 micrometer wide device. This is like 50 micrometer, this is a 10 micrometer, okay, and this is how the I is equal to the second plateau was positioned and the error between various devices. Here, this is also the fourth plateau where error across various devices is in nano ohms, okay. Similarly, here these are done for various materials like gallium arsenide by various labs, and that is their error bar, overall error bar across all the device. Okay, that is in nano ohms. That is 9 place after the decimal. Such a robust phenomena, which is there is nothing better than this to standardize the resistance value. Okay, for metrology purpose. And recently, because of the ease of doing this experiment in graphene and the possibility of doing this experiment at higher temperature, because you have seen that in graphene, you can even see this effect of room temperature. So you don't need a really high-end cryogenic equipment to demonstrate and make this resistance standard. So labs have started looking into fabricating graphene-based resistance standard. Okay, this is one of the devices, and they also have measured the error in this resistance for the graphene-based sample, and they compared that with that for the gallium arsenide. So this is basically graphene resistance minus gallium arsenide resistance standardized over the gallium arsenide resistance plateau. These are the plateau observed by graphene. Okay, and they have found that its accuracy is 9th place after the decimal. Okay. and this is done at 1.3 Kelvin. It's not room temperature, but not really cold either. Okay. And what they found, which is explained very well in this paper here, is the error is again only in nano ohm range, in the nano ohms range. Okay, that is 9th place after the decimal. So now most of the labs have started looking into making graphene as a resistance standard. All right. Okay. Now what we will do in the next module is we'll try to look into the mathematical formalism of the quantum Hall effect, starting with the quantization of these electron orbitals under the action of a perpendicular magnetic field. All right.